Before we formally start 7.3a, I want to talk a little bit about an example that is related to the pennies applet that you just got done doing. So what we're going to do here is look at a population of the ages of these various pennies for a population where it's skewed right. So clearly this population of all these pennies is skewed right. We're going to compare what happens when we make a sampling distribution as the sample size increases. So we're going to look at shape, center, and spread. Here what they've done is they took 100 samples of size 5 and did a sampling distribution, recording the average age. And here they did a sample size of 10 100 times and a sample size of 25 100 times. Now, even though these three sampling distributions were created from a population that was actually skewed, what do you notice about the three sampling distributions in terms of shape? Well, all three of those are roughly symmetric. Okay, how about in terms of center? You're going to notice here the little red number actually computes the center for us. And the center on these are all pretty accurate and close to being the same. So the center is about the same, and it's actually somewhat close to the population mean because the population mean's center was at 12.8. These were all close to 12 point something. And what about the spread? As the sample size changes, as we've been seeing throughout many of our notes, the spread or the variability is actually limited. So there is going to be less variability. This is actually a very important concept as we start analyzing things where we can compute means to them. What if we go beyond pennies and we look at this stealing bases example? So what we have here is a histogram that shows the distribution of stolen bases for 1,340 Major League Baseball players who had at least one plate appearance in 2009. So for example, what does it mean? You know, this particular interval right here, what percent of the players had between 0 and 3 stolen bases? Here maybe that's about 5%. So each bar represents the percent of all of the players and how many stolen bases they had. Now it is interesting in here, this is their actual population graph, and they're telling us here, be careful, the histogram actually goes out to 70, they just cut it off at 20 so we could focus on it more. So it's very much skewed to the right. Okay, so then what they did with this data is they took an SRS 100 times, they used a sample size of 45. So they randomly chose 45 players and then computed the mean for that. When they did it, this was the sampling distribution of the means that they got. Well, what do we notice about the sampling distribution of a fairly good sample size as related to its population? Clearly, the shape of the population versus the sampling distribution, the shape of the sampling distribution is much more symmetric. The center of the information, I will tell you, of both distributions is about the same. And what about the spread? Clearly, again, the spread is less spread out or less variable. So with those two scenarios, let's formally talk about 7.3a. I'm going to show you how to find the mean and standard deviation of a sampling distribution from an SRS of size n. So we're switching gears this time. In 7.2, we focused on proportions or discrete variables. In 7.3, the sample means is this. Sample means are used when we record quantitative variables. What that means is if you read a problem and you're dealing with the variable that's not a proportion but it's quantitative, you can actually compute a mean for it. You have to use this method of finding the mean and standard deviation and ultimately the probability. So let's talk about how they're different. So for a sampling distribution, to compute the mean of all of the little means that we took, it's mu of x bar is how you say this. So the mu of x bar, the mean of all the samples that we took in their mean is equal to the mean of the population, or mu. The standard deviation of all of those little samples is going to be the standard deviation of the population divided by the square root of n, which is the sample size. This is actually going to be true no matter the shape of the population. If the population is symmetric or skewed, we can still use this. Now, we are going to have to make sure that some conditions are met. Like for proportions, we have to check for randomness, independence, and normalcy. So you check for randomness very easily. Independence is actually the same condition. You're just going to check the 10% condition is the population greater than or equal to 10 times the sample size. And then the last one you check is still for normalcy. We'll talk more specifically about how do you check if you have a means and it's a normal distribution when we get to that component of the notes. Overall, do keep in mind though, once you've checked the 10% condition and if it's met, that is what allows you to actually change and create this new standard deviation. Now, if you are taking a sampling distribution and it is coming from a normal population automatically, let me just show you a scenario that was run. This right here is a population of some means that are definitely approximately normal. What they've done here is they took a sample size of 5 and they did it, on this case, over 11,000 times. Notice what happens when they took a sample size of 5 from here, computed the mean, and plotted it. This is a sampling distribution of the means, and it definitely looks approximately normal. What if they increase the sample size to 20? Here we see a sample size of 20, and this was repeated 1,000 times. You're going to see that it's approximately normal. So the thing about the normalcy test when you have the means, here's what we can say. If a population is normal, then the sampling distribution of our X bars is normal no matter the size of a sample. In this case, there is no math to show. For proportions, remember we had to show n times p was greater than or equal to 10. For the means, if we are pulling from a normal population, we are guaranteed our sampling distribution is normal. Let's look at this one example. We're going to a movie. Suppose that the number of movies viewed in the last year by high school students was an average of 19.3 movies with a standard deviation of 15.8. Suppose we took an SRS of 100 students and we calculate the mean number of movies viewed by the members of that sample. What is the mean of the sampling distribution? So what is the mu of X bar? Well, in this case, the mean of the sampling distribution, that's the notation. We know it's just equal to the actual mean. So all we have to say is it is equal to 19.3 movies on average. Now in part B, what's the standard deviation? Be careful, before we can actually state the standard deviation, you must check that 10% condition. The 10% condition on here again is our population greater than or equal to 10 times our sample size. So if we have more than 1,000 high school students, it's independent. So we would just state if there's more than 1,000, we're fine. Therefore, let's go ahead and calculate the standard deviation of the means. That would be sigma of X bar. The formula for this is sigma over the square root of n, our sample size. So if we just pop that in there and we simplify, we now have that the standard deviation of our means is 1.58.